So welcome back. We're going to go ahead and finish Chapter 5 by doing Section 5.9, how do you build exponential logarithmic logistic models out of data? And the objectives are pretty straightforward. If you have data, can you build any of these models? So if you have a scatter plot that looks kind of like this, you're thinking it's exponential with a base larger than 1. This looks like an exponential decay. This is an exponential function with a base less than 1. Okay, which can be a little difficult to distinguish from a logarithmic curve. The main distinguishing characteristic between these two is that this has a vertical asymptote and this has no vertical asymptote, but I'll admit it's not always obvious which is which. Okay. This one has a horizontal asymptote and this doesn't. But with a small amount of data, it might be a little ambiguous what the best model is. Logistic is very easy to distinguish from the others because it has this inflection point where it sort of has a symmetry around it, this S-shaped curve. So here is a chart of data. 0, 35,000, 1, 37,550, etc. Okay. Sorry, so go ahead and copy this down. It's unfortunate. In a physical classroom, we can just write this table on the board, and then there's lots of board space. But these videos, you can't fit very much on the screen at once. So please copy down the table, because refer to it with all of the questions that are coming up. As always, just pause the video to write it down if you need to. OK, so let's take this table of data and answer the following. Draw a scatter plot. Build an exponential model using a graphing utility, because otherwise the best fit is a little tough to find by hand. Take that function and make it look like a normal exponential model, graph that, predict the value after 10 years, and interpret the value of k. So here's how it looks if you just draw a scatter plot. I'll admit it almost looks linear. Okay, but we were explicitly asked to do an exponential regression. And that gives us y is a times b to the x, and they gave us a, b, and then these r squared and r, which have to do with statistics and are not really relevant for us. But if we go ahead and use the value of a and b there we have it. So when that value of r is very close to 1, it indicates a very good fit. That's really all you need to know. So we were asked to take this function and express it in the form a naught e to the kt. How am I going to make this look like it has a base of e? We're going to use a trick we've used before. Okay, so observe that letting t be 0 tells me that the a we were given really is a naught. That is easy enough. In other words, the exponential part needs to equal the exponential part, which tells me that that b is actually e to the k. And there's how we're going to convert this. Okay, whatever b is, it's e to the k. So therefore, this b is e to the k, so we can use that to solve for k. So that tells me that k is the natural log of 1.08, etc., and that gives us a value of k. So now I can convert it to this more standard form of a sub 0, or a naught, which was 34,000 and change, times e to the kt, and we just found the value of k. So there we can graph it. Okay, if we let t equal 10, we just have to plug it in now, and that tells us $78,000. And finally, k, remember, represents the annual growth rate, 8%. Okay, here's another chart of data. Go ahead and copy it down. We're going to have to do some very similar things. We're just going to fit it to a logarithmic curve in this example. So pause and copy this down if you need to. If you have the book, it's in here. It's example 2 out of section 5.9. Okay, so use a graphing utility, draw a scatter plot. If we assume it's logarithmic model, use a logarithmic regression to find what logarithmic function it is. Draw that function, predict the height at 560 millimeters of mercury. That's your input value. And finally, oh, I guess that was it. So we enter the data. There it is. We use a logarithmic regression, and it tells me a plus b ln x, and it gives me the value of a and b. And again, it gives us a value of r, which is very, very close to 1. Okay, so here is our function. We took a plus b ln x. Notice that b is negative. So we have 45.78 minus 6.9 log p. Okay, r is very close to 1, so this is a very nice fitting function. As plotted, it appears to go through those points almost exactly. So then if we want to predict the height of the weather balloon at 560, all we have to do is plug it in, and it evaluates to about 2.1 kilometers. Pretty straightforward. So the next example has to do with a logistic function. So again, here's a big chart of data. Pause and copy, or just open your book on another screen, or if you have the physical book. This is example 3. Well, we're going to have to draw a scatter plot, build a logistic model, in other words, use a logistic regression, graph that, and then we want to ask what's the carrying capacity, and then what is the amount at time t equals 20. So there's our scatter plot. Yep, we've got that characteristic S-shaped curve of a logistic model. We used logistic regression, and it tells us c over 1 plus a times e to the minus bx, and it gives us a, b, and c, and this matches the form of the logistic model that we've used before. And so there it is, taking their value of a, b, and c. Plots very, very nicely. The carrying capacity is just that numerator of 663, and if we want to know what the amount is at time t equals 20, we just plug it in. And we have gone ahead and plugged in t equals 20 down here, which evaluates to 662. It's very close to the carrying capacity. At time t equals 20, we're way up here. We have already gotten very, very close to the carrying capacity. So that's just a couple examples of using technology to find curves of best fit. I've mentioned in passing that, like, when it comes to exams, we don't give you problems that absolutely require a calculator. So questions like this don't show up on exams, but they are very handy if you're interested in applications of this material. So it's nice to go over it. But because on a testing level, it tends to just be, could you hit the buttons correctly? We don't usually ask it on a final exam or something. But hopefully you found it, kind of interesting. And if you're interested in scientific applications, you generally don't have a nice exact formula. What you have is a bunch of data that almost matches something, and you need to know what does it almost match. And so you need to do those regression analyses. Anyway, that was chapter 5.